Have you ever wondered how the fuel that helps aircraft weighing hundreds of tons fly across oceans is actually very similar to the substance that was once used to light oil lamps more than a century ago? That substance is kerosene. Meanwhile, gasoline, a fuel that is more powerful and even cheaper, strangely does not seem to be used for modern jet aircraft. At first glance, this sounds completely illogical. But once you understand how kerosene is produced and the unique properties it possesses, you begin to realize that it is almost the perfect fuel for airplanes. So how is kerosene produced, and why do airplanes use it instead of gasoline? First, we need to look at the nature of this fuel. Kerosene is actually a fraction of crude oil that is separated during the distillation process. Appearing in the distillation range of roughly 180 degree to 260 degree, it sits between gasoline and diesel fuel. Interestingly, in the 19th century, before petroleum refining technology from crude oil became widespread, people actually distilled kerosene from coal and used it to light street lamps and oil lamps. Initially, kerosene is separated from crude oil, a liquid substance extracted by drilling deep into the ground or beneath the ocean floor. After it is pumped to the surface, crude oil is transported to a refinery, where it is cleaned to remove water, salt, and other impurities. Next, the oil is fed into a fractional distillation tower, the heart of the refinery. Here, the crude oil is heated to around 300 and 5400 degrees. As it vaporizes, the different components of the oil separate according to their different boiling points. Lighter substances rise higher in the tower, while heavier substances condense lower down. As a result, many different types of fuels are separated, from LPG, gasoline, and naphtha to kerosene, diesel, and fuel oil. Kerosene condenses roughly in the middle of the tower, in the temperature range of about 150–250 degrees. However, it still cannot be used immediately. Kerosene must go through further refining steps to remove sulfur and other impurities, and then special additives are introduced to prevent freezing and corrosion. Only at this stage does it become standard jet fuel such as Jet A or Jet A1 used for aircraft. Meanwhile, the portion of kerosene that does not meet the required purity standards will be used for more ordinary purposes, such as lighting, cleaning, or lubricating rusted metal parts. You may not know this. From one standard barrel of crude oil, which contains about 159 liters, only around 10% becomes kerosene. The remaining portion is turned into gasoline, diesel, liquefied petroleum gas, and many other products. And someone once said to me, gasoline is also made from crude oil. It also goes through distillation and complex refining processes, and it is a powerful and widely used fuel on land. So why don't airplanes use gasoline instead of kerosene? First, gasoline is far too volatile. At an altitude of about 10 kilometers, where the air pressure is much lower than at the Earth's surface, gasoline can evaporate far too quickly. Part of the liquid can turn into gas, creating vapor bubbles inside the fuel lines, a phenomenon known as vapor lock. To make this easier to imagine, picture a straw that is drawing water but is filled with many air bubbles. In that situation, the water will no longer flow smoothly, and sometimes the flow can even stop completely. The same thing can happen in an aircraft's fuel system. The engine requires a continuous flow of liquid fuel in order to burn properly. But if too many gas bubbles appear inside the fuel lines, the fuel will not flow steadily to the combustion chamber. When that happens, the engine may suffer from fuel starvation or could even shut down in midair, creating an extremely high risk of a serious accident. Second, kerosene is a safer fuel. It has a higher flash point, which means it is harder to ignite than gasoline. One thing that is easy to misunderstand here is that the flash point refers to the temperature at which the vapor of a liquid can ignite when exposed to a spark. Here is a very simple example. If you pour gasoline into a small cup, even a tiny spark or a bit of heat can cause it to ignite. Because gasoline has a very low flash point, around 43 degrees. That means that even in cold weather, gasoline can evaporate and ignite very easily. In contrast, kerosene has a much higher flash point, typically around 38 degrees to 72 degrees. Because of this, it evaporates much less easily and is far harder to ignite than gasoline. You usually have to heat it up quite a bit before enough vapor forms for it to catch fire. Perhaps the most surprising fact is that a large aircraft can hold about 180,000 liters of fuel. A long-haul flight, such as from New York to Tokyo, can consume nearly 100 tons of fuel. This means that the weight of the fuel can sometimes account for nearly 1/3 of the aircraft's total weight at takeoff. If the fuel were as easy to ignite as gasoline, the risk of fire or explosion would be extremely high. Kerosene, however, is far more stable, making it much safer to store and operate within an aircraft. Another issue is the extremely cold temperatures at high altitude. When an aircraft cruises at its typical flight altitude, the outside temperature can be colder than an industrial freezer, about -40 degrees to -60 degrees. If the fuel were to freeze, it would become similar to wax inside the pipes and would no longer be able to flow to the engine. For that reason, jet fuel is specially engineered so that it can remain in a liquid state at around 47 degrees, ensuring that it can circulate reliably and consistently throughout the entire flight. In other words, aircraft fuel is not simply ordinary kerosene. It is a type of fuel specifically engineered for the sky stable enough so that it does not evaporate easily, safe enough to reduce the risk of fire or explosion, and durable enough to keep functioning in the harsh cold at altitudes of tens of thousands of meters. But that is not everything kerosene can do. Few people realize that before it is burned, kerosene or jet fuel is also used as a cooling substance for the engine. Inside a jet engine, certain components, such as the combustion chamber and the turbine, can reach temperatures of more than 1,000 degrees. Without proper cooling, the metal parts in those areas could overheat and become damaged. Because of this, before the fuel is injected into the combustion chamber, it flows through pipes that run near extremely hot sections of the engine. As it passes through those areas, the fuel absorbs some of the heat, much like how coolant helps prevent a car engine from overheating. In this way, critical components of the engine are maintained at a safer operating temperature. Therefore, kerosene was not chosen randomly to become the fuel used by aircraft vehicles that must operate under some of the most extreme conditions ever engineered by humans. From the complex production processes inside oil refineries to the extensive research on safety, volatility, and the ability to function in extremely cold environments, everything ultimately leads to the same conclusion: kerosene is the most suitable choice for the sky.